All right. Looks like we're recording. Great. So very briefly, welcome everyone. My name is Rogers, and for the record today, we're going to be discussing a paper by uh, Hugo Richard, and the name of the paper is Multiview ICA, and I'm going to share my screen with you so you can see some of the slides we put together. There it is. No, one has to go into presenter mode first, and then I can share. There it is. Can everyone see it? The slides, I mean.
Yes.
Awesome. So the name of the paper is Modeling Shared Responses in Neuroimaging Studies through Multiview ICA. It's a paper by Hugo Richard, published in the RIPS last year, 2020. And today we are going to be discussing it. And just briefly, for context, we're using the role-playing seminar format, where we have the following roles, and different people are going to be taking different roles and to give us different perspectives about the work that we're discussing. So today I'm going to start. I'm going to be taking the role of scientific peer reviewer. And as such, I basically went ahead and read the paper, took the review content recommendations from the NeurIPS conference, and they have about 10 to 15 points that they ask reviewers to fill about the paper. And I just summarized my perspectives about it as if I was a reviewer. And at the end, part of the role is giving an accept or reject and justification as to why. And this is more, not intended to criticize the work or anything. It's more of an exercise. Today, of course, I have experience with that, but other students in the future that want to take the opportunity to get some practice reviewing papers, this is going to be a good opportunity for them. And so this is like just an example of how you could go about approaching a paper. So the idea then, I'm going to start with a summary and contribution of the paper, is that it's basically it provides a principled and closed form approach to group independent component analysis with noisy sources and a closed form likelihood. And I have here in my next slide, I'm going to come back here later. Just for comparison, this is from my talk last month when I was just talking about subspaces and comparing different methods and trying to show how different methods relate to each other. For comparison, here is the group ICA model. In group ICA of fMRI, for example, this would be each one of these gray squares would be the fMRI time series of a given subject, typically resting state, but not restricted to that. And you have time along the rows and spatial maps along the columns. And so for group ICA or group PCA, the idea is basically that you stack all the time series from every single subject together in a big matrix, and you find an ICA decomposition with shared sources for all subjects. And I had mentioned in that initial talk, this kind of connection is typically referred to as hard linkage. where the link between the datasets is here through the source, which here is called hard linkage because it's assumed to be identical across all subjects. And another point here is the fact that some models, like probabilistic ICA, assume on top of that that there is sensor noise, that the data is corrupted by noise. Okay. Oh, and I also have a mention here that the method typically for group ICA, it estimates subject-specific sources. So after the fact. So after the method estimates group components, it goes back and use back projection or dual regression to try and estimate subject-specific sources. So there's a post hoc sort of afterthought that where they in the second step after ICA is done, where they try to somehow project the results back into the subject-specific data and get subject-specific components or sources. And for comparison with Multiview ICA, the idea is that I forgot to put parentheses on this figure, but it's all right. The idea is that the sources now have an additive noise to them. So the model directly estimates subject specificity as a difference from the mean source or the group source directly into the model. And by directly into the model, I mean that there is a closed form likelihood that is optimized to account for that. Because it's assuming that still the sources are identical across all subjects, I still classified it as a hard linkage model. But in this case, it has a built-in compensation, is what I call this. This built-in noise on the sources from each subject that characterizes or tries to characterize the variability from the mean and capture subject specificity. So in reality, I think from what I understood, you not only estimate the mean source over subjects, but you also get subject specificity by adding this noise at the subject level, which is estimated together with the model. So it's a source noise model, is the idea. So going back to my first slide, the other contributions then are that, like I mentioned, the source noise serves to capture subject-specific variability. The method uses an alternating quasi-Newton optimization approach, where it's alternating in the sense that there are weight matrices to be learned for each subject, and they are learned one subject at a time. So for every iteration of the algorithm, it iterates through each subject, and at each subject there is an update before you go to the next subject, and then you take the data from the second subject and update the model for that second subject, assuming that the other subjects are subject information from, sorry, the weight matrices from the other subjects are fixed. And so in that sense, it's alternating. It's updating sort of portions. If you think of the full weight matrix, it's updating portions specific to each subject at a time. Yeah, and at the end, they apply their method to, they have several applications, but from what I gathered, they were all focused on temporal group ICA. where the concatenation actually happens in space domain. So it's concatenation of voxels, and the components are time series. An interesting point is that these applications that are in the paper, specifically the fMRI one, they are uh, looking at very long time series. So it's people watching movies. So for example, they have people watching Forrest Gump. And so its resting state, quote unquote, it's actually natural stimulus. They're watching a movie and they're being scanned as they watch the movie. So these time series are really long. It's 2 hour long. So that's the observation here. It's not the typical group ICA where you have 5 minute resting state fMRI and maybe the time series is too short for ICA decomposition. This is temporal ICA with very long time series. So for strengths, the first one is they have a closed form likelihood. I'm not going to go into the details, but we can discuss it later if there's interest. So they have shared sources, and the shared sources are the average over the subject level sources, and it's also built into the model. There is a good quasi-Newton implementation of the method, and that's not very common, so I like that very much. The math and the writing and the intuitions in the paper are really good. There are many applications and comparisons beyond fMRI, including MEG datasets and others. One thing that is mentioned in the paper, but it can be underappreciated, but shouldn't. It's very interesting, is because they have this built-in noise model. It effectively it can avoid second level data reduction, and I think that's a very important strength. It's not highlighted as the key feature of the paper, but I think it's one of the key features of the paper. Yes, and because they are applying this Gaussian noise assumption on the sources, it gives them the ability to write a closed form likelihood for the data, and that's extremely that's extremely unusual, let's say, for ICA methods to have that. We usually just write the likelihood for the sources and don't actually get to fit to the data, fit a likelihood to the data as you would normally with traditional statistics. And I think Carlos had a question.
Yeah, can I make a question
Yes.
of one of the points that you mentioned on the strengths?
Yes.
So, what is that like second level group data reduction? Could you explain a bit more about that? I'm not familiar with that
Yeah. So
concept.
very quickly, just go back here to this figure. It's basically one instance. There are many discussed in the paper, many ways to do it, but one instance is group PCA, where you stack the data. And in typical spatial group ICA, or group ICA for spatial components, you would stack the time series of each subject in literally you load the data from one subject, load the data from the second, and you stack the two into a big matrix. And you keep doing that for all subjects. You get a really huge matrix, and you apply a group data reduction on those concatenated matrices. That's the standard way to do group ICA. once you get the group reduced principal components, then you apply ICA on that, and you get group ICA results. So what is common is to apply subject level PCA as pre-processing. So you take the data from a single subject and reduce the time series from, I don't know, 200 time points or 100 time points down to, say, 50. Then you do the same for every subject, and you stack those 50 components from each subject into a group matrix. And you, on that concatenated stacked matrix, you apply PCA again before you run ICA. So that's the second PCA. That's the second level PCA, group level PCA. The first level PCA is typically understood as pre-processing, like data cleaning. And whether you whiten those components or not is considered an option, and there is open debate whether you should or shouldn't do it. But that's not a tangent already. The point here is that with the model, the Multiview ICA model, they can bypass that second group level PCA step, which is very interesting. So some of the weaknesses that I highlighted here are that yeah, like I mentioned in the beginning, this is a series of applications on especially fMRI for temporal ICA. And temporal ICA for fMRI is very tricky, to say the least, in the sense that the time series is too short. There are too few samples, basically, too few time points to appropriately estimate independent components. And so that issue was not discussed, at least I didn't see in the results, a comparison with that case where you don't have such long time series for fMRI. And I wonder if the other benefits of having a likelihood and closed form likelihood and quasi-Newton optimization would have at least improved or showed some promise in that case. Along those lines, I didn't see comparisons with the more traditional spatial group ICA case. Would have liked to see a comparison there, just to see what kind of source variability comes out of it at the subject level. The alternating update, there was some discussion that ICA is a non-convex problem. Therefore, the best we can do is find local optima. So that local optimality argument is valid and is used to justify alternating the updates subject by subject. But I wonder if the updates were made after you had computed all subjects at once, after you had computed the updates for each subject, if that would have somehow changed anything in terms of convergence or whatever. And I didn't see that kind of analysis. Just a caveat here, there was a lot of work done. So this is not a critical failure. It's just something I would have appreciated because I appreciate those details about optimization. And the last thing is that the noise covariance is basically the same as the data covariance at the subject level. At least that was my understanding. There's a statement about that. And which means that the mixing matrix, the ground truth mix matrix for each subject, basically dictates what is the covariance of the noise. And I have the impression that not all subject variability can be explained by that kind of model. And the same argument could be made about the Gaussian noise assumption on the components. I wonder if that's, I don't have great confidence that all of possible subject variability from the mean component map or the group component map is going to be sufficient to capture all of that possible variation. I don't know if a Gaussian assumption would be sufficient. In terms of correctness, the math seems all correct and well-rounded. I did not verify the Hessian approximation formulation, but I've seen similar before, and it did look correct. And the likelihood I did verify, and everything was correct there. The writing was definitely great. Yeah, I sort of, I'd have liked to see comparisons with the spatial group ICA. I already mentioned that. But other than that, it was fine. Relation to prior work, there's good review of prior work and comparison to those works. I think it missed some comparison with spatial ICA, heavy focus on temporal ICA case, which is okay for the application that they were interested. And just reinforcing temporal ICA means concatenation in space over voxels, not time. Which I think is the least common case in fMRI data, particularly. And the work is reproducible, code is available, but I did not look into that particularly. In terms of score, I gave an 8.5. I was, there's no 8.5. There's either 8 or 9. So, which is basically clear or strong accept. The work is really good. My key issue was really the lack of comparison with spatial group ICA. Other than that, there were no other issues with ethical concerns or anything like that. And yeah, it was a massive amount of work that they put in there. And I think it's a very, very good submission worthy of acceptance. And I think with that, I will finish my part. Are there any questions from anyone? Going once? Going twice? All right, so we'll move on to Carlos. Carlos, you can go ahead.
Okay, so yeah, after read the paper, I didn't read the appendix, just like the main paper. After reading that the paper, I came up with this imaginary follow-up project that is purpose of this role. So I propose a project apply to epileptic echo data for seizure prediction. So the hypothesis is that if you look at if you apply this, you look for those shared sources on the preictal and the interictal state of an electroencephalographic recording in an epileptic patient, you will find that those sources are significantly different. You compare those sources on those two different states. So I propose some methods to quantify what do I mean by significantly different. So first, I have to take the data, this electrocorticographic data, and split it into preictal and interictal segments. Usually, the preictal segment is just before when the seizure starts, and is usually 1 hour long. And the interictal segment is far away from the seizure, like let's say 4 hours away from the seizure. That's kind of like the baseline, the interictal segment, what you would call normal activity, right? And the idea is that if you are able to discriminate between those two type of segments, preictal and interictal, you will have a good basis to build an algorithm for seizure prediction. If you're able to identify between those two type of segments. So what I propose is to use Multiview ICA on those two type of segments, like you will have like two type of data for this for each patient, and then you will use the Multiview ICA, let's say, for the preictal data on across subjects to find what is the share, what are the shared sources among the different subjects for the preictal, and what are the shared sources across subjects for the interictal, and then extract some features from those two sets of sources and build a classifier to quantify how different are those. If you are able to get a good classification performance, a classifier that is able to classify between preictal and interictal using features that are extracted from those sources, then we could say that there is an important difference in the sources that you find in preictal versus interictal. Yeah, I mean, there are a lot of details that I will have to elaborate in this imaginary project, but this is like a starting point, I guess.
Good. Did you consider the, like, what did you consider whether you want this to be like in the interictal phase? Do you want this to be subject level ICA or group level ICA? Which one did you have in mind?
I was asking that myself as I was writing this, and it's like I guess that I'm mostly interested in the shared sources in the preictal phase, because if the hypothesis is that if you're taking data from epileptic patients that are having the same type of seizure, you will expect some sources that are common in the preictal phase that are indicative of a seizure that is being generated, right? But maybe in the interictal part that is more like normal activity, you will have more variability. So I'm not sure if I should like treat those two phases differently in terms of like how do I apply ICA. And the other thing is that maybe the sigma parameter that is used in Multiview ICA could be also different. I will guess that the sigma parameter will be higher in the interictal phase if we were to use this group level ICA with Multiview ICA. Yeah.
Yeah, one thing that I forgot to mention is in terms of like inherent, call it inherent synchronicity across subjects. in the case of say, well, fMRI study where patients were watching a movie, because they were watching, all patients were watching the same movie beginning to end. You can think of the movie as a stimulus, like not like a naturalistic stimulus, right? And a stimulus that is identical to all subjects. So you would expect, to some extent, that the temporal fluctuations on the signal are very similar, if not the same. Or at least at the source level, you would expect that across subjects. And I think that is one of the key enablers of the approach for temporal fMRI. It's not only that the time series is very long, but it's also that you can do spatial concatenation and find a common time series. Because otherwise, if it's resting fMRI, right, two subjects are very unlikely to have the same time series. Their mind wandering differently, right? It's two completely different independent activation sets. But in the case of subjects having the same external stimulus, then it enables, or it makes it the assumption that the time series is the same across subjects more reasonable. And I think that's the point I was trying to imagine if in the pre-ictal portion, if you can also make that assumption, or if you would maybe stack the data differently to be able to extract the time series. I think that might be a reasonable. I'm mind wandering now, but I
Yeah,
don't know if I make sense.
yeah. No, it makes sense, and I think that is a hard question because I mean, if you look at the literature on seizure prediction, this 1 hour segment just before seizure is just like a suggestion. I mean, people,
Mm-hmm.
I mean, we still don't know really where the what we call prediction actually starts. So there is not like a clear cut time that we can say, okay, this is what you should like really call predictal, where predictal should start. I mean, it's just what one of the two main Kaggle competitions have used. So that's,
Got it.
but yeah, it's not like, it's more like a common practice, but there is not like a hard evidence that says, okay, that's
Mm-hmm.
that is where the right timing uh, for looking for these type of patterns are is starts.
Mm-hmm. Awesome. Thanks for sharing the idea. Appreciate it. Does anyone else have a comment on this idea, or any other comment before we move on? Okay, so Kristen, you can go on, and
Sure.
all right.
All right, so this is still pretty new. When I look to see how many times it's been cited 5 times from what I saw. And part of that is, a very good review or a package in Python called Multiview Machine Learning. I don't use Python very much myself, but it's always good when there's a package to go along with a new method.
Right.
There is a PhD candidate, Lacoste. I think he's located in Germany now, who cited this, and someone else, I can't pronounce that last name, it kind of mentioned in passing as, the advantages of subject level augmentation. But the largest influence was a follow-up paper from Richard himself, which just came out this year, called Adaptive Multiview ICA. And so the difference there is that the current paper assumes an identical noise variance across the sources, but then for the adaptive one, now we have an additive Gaussian noise so that you can have different noise sources. And since the author is here, you can correct me if I'm wrong, but I think that was the biggest difference there. And of course, that this paper had most of the influence for the follow-up paper. And for inspiration from older papers, this was a little bit more difficult for me to answer. I felt like conceptually, group ICA, there were several citations with Dr. Calhoun's group ICA methods, but then a lot of emphasis was placed on the algorithms that were used. Being like a mathematician, I really appreciated the closed form of the likelihood and how well everything was written out. And I really had to stop myself from like writing it out myself to check. But like Rogers, it looked pretty good to me. And so I think algorithmically, maybe like Infomax and the relative Newton method papers were probably used the most, since this paper was very heavily focused on the optimization techniques. And I too felt like maybe there should be a comparison with the group information guided ICA.
Yeah, that's an interesting point to bring. I didn't even consider that particular paper, the Gig ICA paper, comparison specifically, because that one is bringing in a prior, right? So it's definitely important comparison, but it's in some sense kind of an unfair fight, because that one, it's taking in some prior information. It's still like, if you consider specifically the case of group ICA, which is probably what you're thinking, right? Running group ICA first and then using those results as prior for subject level ICA, then in that case, I think I'm in agreement. It's a good comparison to do.
Yeah.
Yeah, in fact, I have a follow-up on that. I was going to wait until end, but since Christy brought it up, so I haven't read the paper yet, to be just like as a confession. But when I'm looking at the algorithm one in the paper, please correct me if I'm wrong. What I understood was, so what they are doing instead of like a group level ICA that we do optimization in one set of data, they are doing iteratively and they update the weight for each data set, like they have n data set, right, n subject, and they updated the weight, and then they update the group level sources, right? It's kind of like a moving average, for example, if I understood it correctly. So what I'm trying to understand is, if this is correct, if my understanding is correct, what's the benefit of doing this rather than getting the group level result and then try to estimate the subject level or data set level specific, like what the Gig ICA is doing?
Do you want to take that one, Chris? Kristen? I don't know. I don't know which way you prefer, but Kristen.
Oh, Chrissy, yeah, that's fine. I mean, that's the same question I think that I'm asking, so I'm not sure how to answer it.
I would take a guess, and then maybe we can move to Hugo himself, let him give it a shot. But my understanding is that it's kind of like the essence of the model, that you are learning both the subject average and the subject specific components together. I may be saying it inappropriately, that it's learning the subject level components, because it doesn't quite learn the noise per subject. I mean, it's I can't find the right words to say. But it's go ahead.
I just try to understand. So the way I see a noise, it is a noise, but it's kind of also considering subject variability, right? It's not just a noise, at least the way I see it.
No, it's intended to be a measure of subject level variability. Yeah. Why don't we go ahead and ask Hugo to jump in and give the clarification on that point?
Yes. So indeed you have the so in the model you have only the shared sources that you're trying to learn. So and the parameters of the model are the unmixing matrices. And so once you're able to learn unmixing matrices, of course you can just invert so project the data in shared space. And when you do that, you recover some kind of subject specific sources. But in the model, what you recover is actually the common source plus some noise. And indeed, you can assume that the noise is either noise, and so something that is not interesting because you're interested in the common sources, which in that case you can recover with so you have closed form formulas to recover the shared sources as well. But if you're interested in group specific sources, it also gives you something like that. But in the model, it's actually modeled as noise, even though you can have any interpretation possible of what this noise term really means. And so somehow you can use the unmixed data as subject specific sources. But these subject sources will be close to the sources of other subjects as well.
Yeah, and I think it goes back to that subject specific covariance that equals a transpose, right, for each subject. That's the amount of noise, right, that is captured per component, or the noise structure that is captured. Am I saying it right?
So, I'm not sure I completely understood your point, but so when you have the unmixing matrix of one specific subject, it indeed gives you some information about the covariance the covariance of the noise. And so indeed you have some information about this subject through this.
Yeah, that's what I was referring to. That the the mixing matrix of each subject effectively determines the covariance of the noise for each subject, and then that it's built into the model that affects what kind of variability the model can capture on the subject specific sources.
Yes, exactly. I think you're right, and this is indeed a weakness of the model. So that not all variability can be captured by the model, because the model needs to be simple in order for it to be tractable. So you always have a trade-off between what you can assume, about the complexity of your model and how fast you can estimate it. And so in Multiview ICA, I think you have a nice thing is that the model is very simple. So of course it cannot model anything, but on the other side, it is very fast to fit, and it is also well principled. And I think you cannot have that if you have a model that is too complex. So mentioned by Christy, I think in the follow-up paper we actually show that that you can learn this subject specific noise and have a noise level that is a bit more complicated than the one we have in Multiview ICA. And if you do that, so it's not just about a noise that is a bit more general. It also allows you to estimate Gaussian sources, and this is something that is impossible to estimate with Multiview ICA, or at least in principle, because the noise is assumed to have the same magnitude for all subjects. And so this is clearly a weakness of the model.
Right.
So is Multiview ICA a generalization of Infomax then?
Yeah, definitely, because in info, so if you take the likelihood of, I think it's clearly stated in the paper, but if you take the likelihood of Infomax, if you take Multiview ICA with only one subject, basically you recover the loss of Infomax. So it's exactly the same. It's just that the density of the sources is just a smooth version of the density. But other than that, it's exactly the same as Infomax.
Thank you.
Thank you.
Yeah. Does that get to your question, Armin? Awesome. So then I guess I have my big question, and because we're running out of time, but my big question to Hugo would be, did you in the new paper, or are you considering in future work making a comparison with spatial group ICAs, like where you would do temporal concatenation and estimation of spatial sources instead?
Yeah, I think this is indeed a very good suggestion, and so we should do that at some point. So we didn't do it yet, but I think it should apply correctly to spatial ICA as well. It's just that you will have so you just so actually in principle it's very easy to apply. You just have to apply Multiview ICA and transpose data. So you just transpose your data, and instead of applying them on data that are voxels times the number of time frames, you just transpose it and apply it on the same data, and normally it should work. It's just that the underlying hypotheses are completely different, because you assume that the spatial maps are common across all subjects. So the sources now are spatial maps, whereas the mixing matrices capture temporal information. So conceptually it's quite different, but actually in practice it's very simple to apply. So I think we should do it.
Cool. Yeah, I think I would be very interested in seeing that result and how it compares. We have, especially here in our group, we have a lot of expertise in simulation and just a lot of spatial ICA applications. So I like to see a comparison. Yeah. All right. I guess we are running out of time, but I'll open up for one last question or general comment. How did you guys like the session? Maybe do you want more of this? Should we tweak it a little bit, make it longer? What are your thoughts? Anyone?
I really like the roles. Like, I don't know why, but it just was fun.
It is, right?
Yeah,
like
yeah.
it too.
So I'm wondering when the next one is.
It's probably gonna be in a month from now, end of July. I haven't picked a date, and I haven't picked the list of papers. I'm planning to have like 2 or 3 choices and have people vote on it, just to make it more democratic, other than me, picking up what I like. So yeah, it should be in a month. Do you think? Does anyone else have any other comments?
I also enjoyed this experience. Thanks for the invitation. And I was wondering if since Hugo is here, we could make the questions about the private investigator.
I mean, we could. I don't have them with me right now, or do I? Maybe.
So yeah, is where have you worked
No.
before, right? Oh yeah, yeah, you have.
There it is. So Hugo, I don't know if you have the time, but I guess we would be curious if you could answer a couple of these questions to us. Would you mind?
I'm sure.
Specifically, this one here. Where have you worked before? What did you study? What's your background? Your previous projects, and what motivated you to pursue this?
So actually, I'm a third-year PhD student. So I've only worked on in my lab in France at Paris. And so, but I had previous project before, and so one of my previous project is about is actually still about shared response, but under orthogonal constraints. So you have some literature about a shared response model that was submitted at NeurIPS 2015, about a model that does actually almost the same thing as Multiview ICA, but it works under orthogonal constraints. And the good thing about orthogonal constraints is that you can have a very fast algorithm. And so one way to see Multiview ICA is just to so they also do temporal but they also work in they also do temporal group ICA, even though it's not an ICA algorithm, but they are basically studying the same thing as what we did in Multiview ICA. So one way to see Multiview ICA is just to see it as an extension of this work that works under orthogonal constraints. And so basically, so I've also worked on data augmentation and stuff like that, but it's a bit less related to the current topic. So yes, I think that's it.
Okay. What did you say was the name of that method? I didn't get it in the beginning. Something with orthogonal constraints. What was the name of the method? So I'm sorry, I'm not hearing you, Hugo.
Oh, can you hear me now?
Yes, yes.
Okay, so the method I've worked before was called shared response model, so SRM.
SRM. Yeah.
And so basically, it's exactly the same model as ours, but the mixing matrices are assumed to be orthogonal.
Got it.
And
Got
yes, so actually, it has a lot of success because it's kind of based on the previous work by Axby on a hyper alignment. And so it's kind of trendy in hyper alignment to work with orthogonal constraints. And so one way to see our work on Multiview ICA is just to see it as a variation on shared response modeling, but without the orthogonal constraints. And we actually see that it works better in practice. So yeah.
Yes, I agree with that. Got it. Yeah, I read the references about SRM in the paper. Thank you for clarifying. Okay, so let's start wrapping up then. Thank you so much to everyone who attended. Thank you for the feedback. If you have anything else you want to share about the format, especially if you think it needs to be longer, we are already 10 minutes past. Let me know. Feel free to fire away in the Slack channel. And other than that, I thank you so much. Thank you, Kristen. Thank you, Carlos, for putting the time, prep the slides, and presenting today with me. And next time, after we pick the next paper, please, let's get more people to join. I think it should be fine to have more than one people working on the same role. We should give that a try at least once and see how it goes. And yeah, let's just get to do more of these. I enjoyed it, and I appreciate your time very much. Thanks, you.
Chris. Good work.
All right. Thanks, guys. I'll stop sharing and I'll end the session so you can exit if you want. Thanks.
Thanks
a lot.
Bye.
I just have a question if people hasn't left yet.